Everyone. Today we are discussing about inductance. Inductance is denoted by letter L and its units are Henry. Yeah, basically, inductor is represented like this. The inductor's property is to oppose the rate of change of current. That means the value of change, the value of current cannot be changed immediately. Uh, it acts as a type of inertia to the current. This is the property of inductance, and from according to Faraday's second law of electromagnetic induction, the induced EMF is proportional to rate of change of flux. Total flux linkage can be n phi. So placing n phi in place of the flux linkage, it is given as v of t is equal to minus n d phi by dt. Here minus indicates it is opposite to the applied voltage. This comes from Lenz's law. Lenz's law, it states induced voltage opposes the cause of its production, that is change of magnetic flux. According to the Lenz's law, if a voltage applied to this inductor, a current flows through it. That current builds a flux. The change of the flux creates the induced EMF inside this coil. So that induced EMF is exactly opposite to the applied voltage. So the cause of the production of voltage is change of flux. So our induced EMF opposes the change of magnetic flux. From the above equation, V is equal to n d phi by dt. We can divide and multiply di. So it can be splitted like this, and the term here is inductor. The negative sign is dropped as we are focusing on magnitude part. Now the equation can be written as V is equal to L di by dt. From this equation, it is clear that voltage is proportional to rate of change of current flowing through it. So the inductor equation from this, we can take it as L is equal to n d phi by da. If we consider a linear circuit, that means there is no saturation. If flux increases, current also increases. In that case, differential form can be removed. L is equal to n d phi by d, n is equal to n phi by I. If we consider a non-linear magnetic circuit with saturation effect like iron cores, the flux is not proportional to the current. In that case, differential form is required. So L is equal to n d phi by di. Now defining our electrical parameters, voltage and current. So V is equal to L di by dt. When we rearrange this, di current will be 1 by L under root of minus infinity to t V dt. So power equation P is equal to VI. If we place here, the equation can be written like this. And if you want to calculate energy stored in an inductor, so energy stored can be represented as power into time. As it is continuous, we can integrate it. So if you place the power equation, dt will be cancelled. So dit will be remaining. So I of t can be written as I. So L integration of I di. If we integrate it, work done will be L into I square by 2. inductor behavior at switching conditions. Let's we take inductor standard equation V is equal to L dI by dt. In the switching at DC, the switching is under DC circuit. So in the DC, the change of current is 0. So the voltage drop across that inductor will also be 0. So at steady state, the inductor acts as a short circuit. If we consider inductor current 1 by L integration minus infinity to T V of t dt. If we consider a switching circuit, the switch is closed at t is equal to 0 the time. The integration limits can be split as minus infinity to 0, 0 to t. So the 0th instant is subdivided as 0 plus and 0 minus. 0 minus is just before the switch is closed. 0 plus is the just after the switch is closed. So if we split the limits, and it can be rewritten as like this, and minus infinity to 0 minus is treated as history value. Again from 0 minus to t, it is the after switching case. So history value can be treated as I of 0 minus, and this is the after switching value. So at the 0th t plus instant, we can written as history value plus 0 minus with to 0 plus. So as we consider an ideal switch at t is equal to 0 seconds, it just operates. So the current from 0 minus to 0 plus will be 0. So this term be 0. So here I of 0 minus is equal to I of 0 plus. So at the switching, just before and just after will be same. If inductor having an initial current I0, then at the switching instant 0 plus, the inductor act as a constant current source with a value I0. If the switch is closed, we can see the switch with this condition at t is equal to 0th second. If the inductor having I0 current, then when the switch is closed, then it acts as a source and it delivers I0 current to the source. At a steady state, that is t tends to infinity, it acts as a short circuit. As the current inside the inductor gets discharged, and the current at t tends to infinity, the current inside the inductor will be source current, as it acts as a short circuit. It just direct a conductor. Series and parallel connection. When inductors are in series, then it can be written as addition of sum of all the inductors. In parallel case, it can be written as 1 by L plus 1 by 1 L2 plus 1 by L3, so on. Under AC voltage equations, then we apply an AC current. So the AC current will be magnitude with sine omega t. So if we differentiate it, Im omega cos omega t. If we write that the same equation in sine terms, so omega t plus 90. As it is a pure inductor, the phase angle is lags by 90 degrees. So V is equal to omega L sine omega t plus 90. If we consider a peak value, then it can be written as V is equal to omega L Im. So omega L can be written as XL, that is reactance. The units is ohms.